Welcome students. Today we are going to study Ultraviolet and Visible Spectroscopy Part 2. In our first video lecture, we have already discussed the introduction, the principle, the instrumentation of Ultraviolet and Visible Spectroscopy. So today we will be discussing two topics, that is theory of electronic spectroscopy and the types of electronic transitions. So let us begin with the theory of electronic spectroscopy. When the molecule absorbs ultraviolet or visible light, its electrons get promoted from the ground state to the higher energy state. In the ground state, the spins of the electrons in each molecular orbital are essentially paired. In the higher energy state, if the spins of the electrons in the excited state are parallel, then it is called excited triplet state. The triplet state is always lower in energy than the corresponding excited singlet state, and therefore triplet state is more stable as compared to the excited singlet state. In the triplet state, electrons are further apart in space and thus electron-electron repulsion is minimized, or we can say it is very less. The absorption of ultraviolet or visible light results in singlet ground state to excited singlet state transition, which is converted to excited triplet state with the emission of energy as light. The transition from singlet ground state to excited triplet state is symmetry forbidden. The highly probable transition due to absorption of quantized energy involves the promotion of one electron from the highest occupied molecular orbital to the lowest available unfilled molecular orbital. In most of the cases, several transitions occur, resulting in the formation of several bands. Now let us study the types of electronic transitions. When a molecule absorbs radiations, the electrons are excited to higher levels. The electron involved could be sigma electron or pi electron or n electron. In the diagram below, sigma, pi and n electrons have been indicated in a molecule of aldehyde. So you can see here are CHO, sigma, pi and n electrons can be seen here. So this is just in one example. So we'll be studying in detail. Now the following electronic transitions are possible: sigma to sigma star, n to sigma star, n to pi star and pi to pi star. So here you can see a diagram in which electronic transitions and relative energies are shown. So you can see the electronic transitions. First is sigma to sigma star transition. Second is n to sigma star transition. Third is pi to pi star transition. And fourth is n to pi star transition. So the symbols are written: sigma, pi, n, pi star and sigma star. And the molecular orbitals are also shown. So sigma and pi bonding molecular orbital, then n non-bonding molecular orbital and pi star sigma star. So these are both antibonding molecular orbitals. The energy required for various transitions obey the following order: sigma to sigma star, then n to sigma star, then pi to pi star, and the last one is n to pi star. A brief description of each, all the four types, is given below. So let us discuss them one by one. So first we'll be discussing sigma to sigma star transition. As you can see, we have just now seen the energy order. So these transitions are of very high energy. Transitions in which sigma electron is excited to sigma star orbital is called sigma to sigma star transition. The sigma to sigma star transitions are of very high energy, short wavelength, and occur in far ultraviolet region. These transitions are shown by saturated hydrocarbons containing only sigma bond, that is alkanes. The UV region below 200 nm is less informative and hence is not considered for practical purposes because oxygen absorbs in this region. Now example is sigma to sigma star transitions are found in all alkane because only sigma bonds and no other molecular orbitals are involved. Ethane and propane show lambda max at about 140 nm and 135 nm respectively. Now next comes the second type of transition, and this is N sigma star transitions. This transition corresponds to the excitation of a non-bonding electron to sigma star molecular orbital. This type of transition takes place in saturated compounds containing one heteroatom with unshared pair of electrons, that is N electrons, non-bonding electrons. Generally, O, N, S and X, that is halogens, are the atoms possessing non-bonding electrons. Some compounds undergoing this type of transitions are saturated halides, alcohols, ethers, aldehydes, ketones, amines, etc. And in sigma star transitions, they require comparatively less energy than that required for sigma to sigma star transitions. And this you can easily understand by the energy order which we have discussed earlier. Now the example, for example, lambda max of vapor of trimethylamine is observed at 227 nm. Now next comes N pi star transitions. Okay, so this is the third type. We have already discussed sigma sigma star, N sigma star. This is the third type of transition. N pi star transition. Now these are the transitions in which non-bonding electrons are excited to pi star molecular orbitals. In short, we can say an electron of unshared electron pair on heteroatom gets excited to pi star antibonding orbital. This type of transition requires least amount of energy out of all the four transitions, and hence they occur at longer wavelengths. Compounds having double or triple bonds such as CO, CS, etc. display these transitions, and weak absorption bands are obtained in the UV spectrum. For example, compound having CO group shows an absorption band at 279 nm due to N pi star transition. And the last one is pi star transitions. So this is the fourth type of transition. These are the transitions in which pi electrons are excited to pi star molecular orbitals. This type of transition occurs in unsaturated centers of the molecule, that is, in compounds containing double or triple bonds, and also in aromatics. The excitation of pi electron requires smaller energy, and hence transition of this type occurs at longer wavelength. A pi electron of a double bond is excited to pi star orbital. For example, alkenes, alkynes, carbonyl compounds, cyanides, azo compounds, etc. They show pi to pi star transition. One example, that is in ethylene, the corresponding lambda max is equal to 180 nm for pi to pi star transition. So we have discussed today the theory of electronic spectroscopy and the various types of electronic transitions. Thank you so much.